In this video, I want to talk about moment. And all moment is how much something wants to rotate around an axis. So if we had a seesaw at this point, and you had maybe some guy standing at the edge, he would be applying his body weight to this at a distance of something. So the moment, in this case, is equal to the force times the distance. So moment isn't just about the force, it's about the distance. So if you applied the same force, so if this guy scooted over this way and say cut the distance in half, so you cut the distance in half, the moment is cut in half as well. So if he was right here, and now we have half the distance, you cut the moment in half. So force is an important thing, but distance is also a very important thing. So how far you're away from something affects the moment, or how far you're away from the axis affects how much the moment will be. So now, what happens if we had a force? So we'll say we have some solid, and we'll call this axis A. So we'll just call that A. And we had some force that was applied in that direction. So it's pulling the object that way at this point C. Now you might be tempted to say, right here is the distance. This is not the distance. This is lowercase r. I'll show why that's important in a minute. But the actual distance is if you took a line, the line of action, and put it perpendicular to some line that's coming from point A, that makes a 90-degree angle. So if you get a 90-degree angle with another line that goes through point A, then this is the actual distance. So you can actually calculate D if you know what R is. So D is equal to R, lowercase r, sine angle of this angle. Now you may not know what this angle is, but you probably know what this angle is. If you know what this angle is, you know what angle 1 is, then you must know what angle 2 is. So all you have to do is know this angle, and you can get D. And if we have D, then we can have the moment, which is equal to the force times the distance, or the force times r times the sine of the angle. So that's all the moment is. So the moment is positive, and in this case, the moment would be positive. So it's wanting to rotate this way, and that gives it a positive moment. So this would actually be positive. But if we applied a different force, if we applied a force that was instead going this way, the moment would be negative. So it would be wanting to rotate that way. So when it rotates clockwise, it's negative. When it rotates counterclockwise, it's positive. Now something else about the moment is we can actually use vectors to see moment, or quote see. So if we had some nut and we had some wrench or something, make it three-dimensional, or my best I can, and we started rotating it this way, and it was rotating around this point, the moment would come out of the page straight up. And if we rotated it the other way, it'd go straight down. So when it goes straight up, it's positive. When it goes straight down, it's negative. So this represents positive, and this represents a negative moment. Now the reason that we actually use these vectors that shoot straight up and straight down is not because this object actually wants to go up or go down. It's because when you multiply the moment, not multiply, but the moment is equal to r times the cross product of f. And we said this was r. So we treated r like a vector. And you multiplied, or not, you took the cross product of r, f. You would get this vector that shoots straight out, up, or straight down. So that's actually how we get these vectors here. It's just because of the cross product of r and f. And this is not equal to f times, or the cross product of r. That gets you something completely different. So you only want to multiply it, you only want to have the cross product of rf, not fr. So that is pretty much the moment. The really important thing is well, at least in the next video I'll go over, is this is the distance that matters. That distance right there is what really matters, unless you're going to take the cross product.